Hi all, good evening. This is Sai Das, your PMR FNP TA, who is assiduously giving making sure that some of the concepts that you go across in biological phenomena are explained in a deeper way. I hope people see the video, at least see the presentations. And as usual, we'll wait for 10 to 15 minutes before continuing on this, so that if in the off chance that someone might log into the meet. By the way, today is going to be well, I think it's tough, but today is it's an explanation of what is called as the engineering Bernoulli's equation, and this one I found interesting. I hope you also do, assuming you watch the videos. That note, let's wait. Let's make the waiting time 10 minutes because we may have some ground to cover today. So let's make the waiting time as 10 minutes today.
Saranga.
Okay, time has run itself down. Let's start. So, as I told you today, we will be looking at the engineering Bernoulli equation. And so this is the engineering Bernoulli equation, alright? So delta P by rho plus delta V square by 2 plus G into delta X or delta Z or delta Y, depending upon your convenience. You can use any alphabet. It represents something. And FL hat, which is the frictional loss per unit volume, and WS is a shaft work. Frictional loss per unit mass, and WS is the shaft work per unit mass. So these two are new terms. I'm sure you may not. I mean, some of you may have, but many of you may not have come across this one. So let's leave it. Leave this as that. But I think you can. The first problem is that match the first three gradients. These are all gradients. When you have the symbol delta, that itself implies that there is a gradient. So match the first three gradients with the respective terms: pressure gradient, velocity gradient, and distance gradient. I don't think I need to wait for this uh, because if by now you should know at least this. So I'm going directly to the answer. So this is the pressure gradient, this is the velocity gradient, this is the distance gradient, and this is the frictional loss per unit mass, and this is the shaft work per unit mass. And what is shaft work? What do you understand by shaft work? So we can say that thermodynamically we can say that it is the work done on the system by the surroundings, but commonsensically, if we take let's say an air compressor, and an air compressor, if you think about it, for all practical purposes, it's a closed system. In that air at the lower pressure enters the chamber, and the air at the air at the outlet, air at the inlet enters at a lower pressure, and the air at the outlet goes out at a higher pressure. And this is done by what you have called as an air end that is present inside the compressor. There are different types of compressors. I'm not going to go into it, but what I want you to understand is that there is an inlet, there is a volume element in which the air gets compressed, and there is an outlet where the low pressure air is the high pressure air comes out. So how is this? So you cannot convert a low pressure fluid, in this case air, into a high pressure fluid. You have to do some work on it, right? And that's where the compressor comes in. That's where the air end comes in. And this air end, the work that is done on the air end, by the air end on the air, this can be said as shaft work. For compressible fluids like gases, typically compressors are used, and for incompressible fluids we use pumps, but the concept remains the same. That is called a shaft work. So now given this background, we will try to understand the flow through a pipe in two aspects. One is this is a pipe. Pipe is a cylinder. This is a horizontal pipe, and we are going to try to understand the nature of the flow of the fluid across the pipe, typically incompressible. Uh, with respect to the first dimension, that is, you take a pipe. So if you take a pipe and you take a small volume element of it, it is a three-dimensional element, correct? Now, if you slice, or if you take a plane within this three-dimensional element and look at this plane, actually it's not one dimension; it's two dimensions. So I will change it in the slide when I upload it. This is a two-dimensional look, an aerial look perhaps. So this is a two dimension, and what happens to this engineering Bernoulli equation is that so V1 equal to V2. What does that mean? While you think about it in the background, I will give you some background on the engineering Bernoulli equation itself. So many of you should have come across Bernoulli's equation in your high school, uh, and I mugged it up. I didn't understand it then. So now I understand that. I understand that, but that is what you should have studied in your high school is that for an ideal scenario, and this is called as the engineering Bernoulli equation because this can be used in practical scenario which deviates from ideality. Think of it as a deviation, like a deviation of most of the gases that we have in this world are non-ideal, and this deviation into practicality happens in fluid flow also. And for this purpose, the engineering Bernoulli equation is derived. It's been designed. To understand the derivation of this equation, you should go and have a look at the transport phenomena book by Dr. Bird, and people who are interested can go into it. But we are not go the but that those derivations are beyond the scope of uh, beyond our scope for this purpose of this lecture. Now, consider the flow through the two dimension, the aerial two dimension. I have put it as one dimension. I will correct it and then upload the slide. And so now, why is V1 equal to V2? What is the assumption? So this is 1, this is 2. What is V1 equal to V2? It's simple, right? It means that the flow of the flow of the fluid across this cross-sectional area is a well developed flow, which means there is no difference in the velocity at any point between point 1 and point 2. So delta V goes to 0, and both the distance element, right? So let's say that you know uh, this pipe is a perfectly horizontal pipe. There is no curve, there are no complications. So the the distance at the point 1, which is for this purpose, let's say Z1, and the distance all the difference in any distance between the points 1 and 2 denoted by Z1 and Z2 is equal to 0. So this also goes to 0, and there is no shaft work that is done. Let us assume that, and we are going to take that also to 0. So this brings us to equation 2, which is FL hat, which is the frictional loss per unit mass, is equal to minus delta P by rho. This is the equation, and what we are going to now look at is we are going to find out what is delta P in the context of the engineering Bernoulli equation. For that, we need to go into 3 dimensions. Before we do that, I have a question for you. Okay, so in this volume element or in this aerial element, assume I use an impeller within the pipe to maintain the uniformity of flow. So just let's assume that to keep V1 equal to V2, I need to put an impeller here and I need to circulate the fluid. So how will there first of all will there be any change in the equation 1, and if so, what will be the change? I'll give you a minute to think about it, and let me know what would be the answer. I'll give you a minute or two. Alright, it's the answer is simple. When I put an impeller into it in a closed volume element, what do? The impeller is used to maintain, as I said, fully developed flow. That was the initial assumption. So the impeller does work on the fluid, on the fluid that flows in this cross section of the pipe, which is basically shaft work. So basically, shaft work won't be zero, and this FL hat would be minus delta P by P minus WS hat. So it's simple. I hope people got it. Now this is also two dimension. Now we saw this kind of an horizontal pipe. Now let's take this kind of a pipe. Okay, where there are some, there's a difference in the element. Let's say this is the volume, this is the aerial element, and there is a difference in, consider this as H1 and H2 to be analogous to Z1 and Z2 in the previous example. How will this impact equation 1? Now, I think I gave you the hint of Z1 and Z2. So basically, Z1 is not equal to Z2, so delta Z is there, so this component will be there, and the equation will develop into FL hat equal to minus delta P by rho minus of G into delta Z. But over and above that, think about this, right? I mean, so So can we do we have to use one equation for this to describe this system, or can we split this equation into more than one more than one can we split the Bernoulli equation, the engineering Bernoulli equation, into more than one type, depending, based on this figure, and would we be able to this if you go through the video, I'm not going to derive everything, it's beautifully derived in the video, so I'm not going to derive it here. So this requires integration. So at one point of time, it will be the equation will be integrated. So when you arrive at the differential equation, can we do something to make our life easier here? Is there something that can split this whole thing into more than one engineering Bernoulli equation that would make it easier to integrate it? It does, right? So split it into three volume elements. From here, H1, let's say now let's go back to the Z notation. The distance here, Z1 and Z2 here is 0, and Z1 and Z2 here is 0. So these two can be defined by one set of equation, and this can be, in this case also, Z1 and Z2 equal to 0. However, uh, we can't say that, right? Well, one thing we can do is to take this and this as one system, this as one system. But if you understand, if you see um, the flow here is orthogonal to the flow here, so the G component will appropriately change, and we can maybe you know define this system in a different way. The place where it turns, or I'll be complicating it. Perhaps then you know we can integrate this as a whole system. This was a thought experiment of mine, so I'm thinking aloud. So fair enough. I think it would make our life easier if we look at it as one system and not as a system of systems, and use the Bernoulli equation appropriately. Now coming to remember when we talked about the flow through a pipe, it was a cylindric pipe is a cylinder, and it was a horizontal pipe, and this was the aerial cross section, and we arrived at the frictional loss per unit mass. And what we now need to find out is the is an appropriate notation for this delta P. How we go about doing that? For that, we need to go into the three-dimensional understanding of this of this pipe. Now consider this cylindrical pipe, and this is the direction of flow of the fluid, and this is the radius of the fluid. Now consider a small volume element, an infinite volume element, and which is whose width is delta Z. Now when you see this, You should by now easily can come to the can understand this figure. So basically, there is a pressure force that is working. I mean, that is moving along. There is a pressure force that is acting uh, uh, along the flow of the fluid, and there is another pressure vector that is at at delta z, at the distance of delta z. There is an opposing force, and at the annulus, not the annulus is not the right word here, at the end or at the surface or the contact surface between the fluid um, and the cylindrical pipe, there is a shear force involved, and that is denoted by tau W. Now, why is the shear force involved, and what is the nature of the shear force? Now, why the shear force is involved, I think you should be knowing it by now. If not, please go and look at my previous lecture or the NPTEL lectures. And now, why it should be laminar? It's very simple. Typically, for any turbulent flow, any given turbulent flow, in a typical case of any fluid in a given system, the fluid flow, as you know, the fluid is be divided. If you remember, if you had watched last lecture video, you should know that you know this it is this whole fluid flow or through the volume is divided into several volume elements, and we are talking about the volume element that is nearest to the surface of the cylindrical pipe. And typically at this interface between the fluid and the cylindrical pipe, the flow is laminar typically. Now I'm not, as I said, I'm not going to derive everything. So using these assumptions, using some integration, as I said before, please look at the lecture video. It's been explained. We arrive at this equation 3, which is the frictional loss per unit mass is equal to is a function of the shear the shear stress dou and the length of the pipe L and the density of the fluid and the the diameter of the pipe. Now we define a factor called as the friction factor. So friction factor, as defined in equation 4, is the kinetic or the kinetic energy component of the fluid per unit area divided by the kinetic energy per unit volume that is inherent for a given fluid at given condition. So I've just defined it now. I know that it is kind of a very vague definition. Now let us break it into parts. Now when a fluid, the force of fluid on a given on a given surface uh, can be divided into two components. One is the static component and one is the kinetic component. Now let's say if the fluid is not moving, we are thinking about a storage tank. There is going to be no kinetic component. There is only going to be a static component. Now here, since this fluid is moving, there is a kinetic component which is denoted by Fk, and Fk is divided by the unit area, and the whole thing is divided by the kinetic energy per volume of the fluid. So basically, this factor represents represents the frictional or instead of over complicating it, this is a factor that has been introduced to our convenience to go downstream this equation, but it's basically the kinetic energy component divided by the volume element or the kinetic energy per unit volume of the fluid in a given volume element. It's as simple as that. I can't simplify this further. I will perhaps I can repeat this once more. This is the frictional, the kinetic, frictional for the force due to uh, the kinetic part of the force per unit area divided by the kinetic energy present in the uh, volume of a fluid that is moving across a pipe. Now, if you take this friction factor and substitute it into uh, you know um, uh, substitute it into the derivation, and that derivation is explained as I said in the lecture. We get this equation, which is the FL hat equal to F into L divided by D by 4. It's given for a purpose as D by 4 into the average velocity divided by 2. So basically, if you think about this, we were dealing with delta V and delta P, etc. before. Now what we did was, what you should understand is that during the course of the derivation of this of this body of work, there was an integration. So this V average represents the average velocity of the uh, fluid over the length of the pipe. The length of the pipe is denoted by L, the D is the diameter, F is the frictional factor, and now we denote now we uh, define another component called as the hydraulic radius. Now what is the hydraulic radius? Hydraulic radius is defined as the cross sectional area divided by the wetted perimeter. Now let's try to understand this figuratively. Now I'm talking, let's look at this volume element, the cross sectional area of the volume element divided by the wetted perimeter of this volume element. So basically, what is the cross sectional area? The cross sectional area is equal to 2 pi r, right? And the wetted perimeter here is basically uh, the perimeter of basically this circle times the width of this volume element, correct? The width of this volume element is delta z. So basically it's the circumference of the circle times the width of the volume element, which is 2 pi r into delta z. Now it is given as d square by 4. So if you put I don't think I need to explain this to you. So area of a circle is pi r square, so d is equal to 2r, 4r square, r and r get cancelled, it gets pi r square divided by 2r pi, or 2 pi r, which is the circumference. Um, um, Sorry, so the wetted perimeter is only the circumference, it's not the volume element. So which comes to d by 4 for this horizontal cylindrical pipe. So why do we define this hydraulic radius? So the hydraulic radius is defined because uh, you, you may not have the luxury of analyzing only cylindrical pipes. There might be non-cylindrical pipes, there might be complex pipes with complex uh, curvatures, etc. So this hydraulic radius uh, normalizes this frictional loss per unit mass to any kind of pipe or a system of pipes, for the sake of simplicity, for any, let's say, for any kind of pipe. And So what happens is that if you basically substitute this into this, you get the FL hat equal to F into L by RH into V square average by 2. So basically, if you know the L can be measured, the hydraulic radius can be measured, the average velocity can be measured because we are the people who are pumping it into the fluid, and if we know the frictional factor, we can find out the frictional loss per unit mass. Now, think about this. So, what is this? How can we get this? How can we know this frictional factor? So, in the lecture, you would see, for a given Reynolds number, what is the frictional factor? There are certain correlations, and using those correlations, a chart has been built. And using this chart, you can, you can find out the frictional factor. So, is it going to be like bang on? Well, it's a correlation. Correlations have their own idiosyncrasies, and not all correlations works best at all time. But for our practical purposes and typical engineering purposes, these correlations work well. So to find out FL hat, we can use basically use this equation. Now coming to the problem solving approaches for the assignment given here. If you go through the assignment, it's not it's very simple, and uh, perhaps I would give you a minute or two to just breeze through the assignment if it's available to you for week 6. um, Still no one, huh? I'm just reminded of this film I Am Legend. I'll keep doing my work regardless of whether people join or not. So if you have gone through the assignments that was available, so basically if you go through the lectures, all you need to do is to match the question with the formula, and you will easily get what you want. For example, um, I don't want to give out any answers for the assignments, but I will put a similar question here. Let's say that in a chromatographic column, there is a flow of fluid, and uh, you know the I'm not going to frame it the same way as is framed in your assignment. I'm going to frame it my own way. So let's say the friction factor is given, the frictional loss per unit mass is given, FL hat is given, and all the others is given. They find out what would be the average volume of the average velocity of the fluid that is flowing through that, let's say a HPLC or a chromatography column. So all you need to do is to rearrange this equation, and take the square root of it, and you get the average velocity. So the assignments or the questions that are present in the assignment are that simple. However, if you think there are certain complexities that are involved in any of your problem solving uh, in during the assignments, I would gladly be of help. So I'm going to, so that with that we finish the a part of the engineering Bernoulli's equation. I'm not going to go through everything. I mean, we don't need to, because it's already there in the LP and Peter lectures. Very well put, and I don't need to, you know, put everything and cram your brain within an hour. All I wanted to give you was an understanding introduction to the engineering Bernoulli equation, and I think I've adequately provided that. And with the miraculous, if any miracle, by any miracle, somebody joins right now for any questions about any of my lectures, including this one, I would be happy to answer them. So I open the floor for questions, the empty floor. I don't know why I put one dimension here. I'll change it. Mea culpa. Nobody. Well, I do hope you understand that though a lot of math is involved in this course, it's not only about math. It's about understanding the system in question. And like any language, math is also a language. So they are using that language to describe the system, so it's a means to an end. So I hope you have, over the course of this course, you would be in a position to better understand systems, you know, in a, in a intuitive visualizing way, so that if you further uh, pursue your studies in biological systems, these things will be of foundational advantage to you, because whenever you think about a reagent being added, a dye being added to a cell that goes inside the cell, and something like that, you would immediately be reminded of certain equations of diffusion, etc., etc., etc. Talking about this whole course, so it will be of foundational significance to you. So I'm not telling you leave the math, understand the math, but please also understand that you're studying not mathematics but about systems. That should always be in your mind. Actually, if you think about it, the frictional factor, right? If you think about it, for a moving fluid, this is basically force per unit area. The force per unit area due to the kinetic energy of the fluid per unit kinetic energy that is stored within the fluid per unit volume, right? This is the force per unit area, this is the energy. So basically, uh, that's an intuitive sense of friction factor. Not that I think about it. as I see, no one has come to miraculously join the uh, presentation. So I would like to close this lecture. I'll change the one dimension to two, and I'll upload the slides and I'll upload this lecture. And I hope people look at it. All right then. Thank you very much. Bye.